Hello everyone. Today we are going to have another practical case of a well modeling using WellFlo software. And in today's video or series of videos, we are going to have a well with electrical submersible pump, but now it's an oil well. And I want to do workover and I want to perform commingle production. So starting from opening only one reservoir, okay, and in that condition I have ESP operating, and later on I want to open another reservoir which is a different reservoir, okay, hydraulically disconnected reservoir, and I want to see uh, how big is the production improvement that I can obtain by opening a new reservoir and combining or performing commingle production. Okay, so I have the model with me. So I'm just going to introduce the model. So yeah, currently we are under the dashboard. You can go to, yeah, if you want to input the data here, you can input the data, the company, well platform, and so on and so forth under the general. And well, and flow type, of course, it's a producer, and I equip my well with ESP. Flow type, tubing, nothing special. Fluid type, black oil, and we have a vertical well right now. Flow correlation, as usual, we start simple using only Dunstros standard correlation. And reference depth, okay, I use calibushing, and the distance between calibushing to the wellhead is only around 6 feet. And fluid parameters, so I have oil gravity of 36 degrees API, which can be calculated, or you know, which is actually oil gravity of 0.84, and gas specific gravity 0.7 with water salinity of 30,000 ppm. No inorganics, and using the water salinity you can get the water gravity automatically. And if you are curious, you can also perform the calculation here. Open this PVT data calculator, just input the properties in. Like in this case, I input my pressure 921.7 psia with reservoir temperature of 180 and produce GOR of 300 SCF per STB. You press the calculate button and you get the information for the bubble point pressure and oil formation volume factor, oil viscosity, and solution gas ratio, BG, and so on and so forth. Okay, you can also get the chart. Like for example, if you're interested in oil viscosity, you can calculate, sorry for the window, it's like this. Okay, so pressure range, for example, upper range maximum is at 921, and lower range, for example, 15 psia, steps 10, and at the same temperature, for example, 180. Okay, and then we can plot, you get that. So the oil viscosity, starting from the reservoir pressure, current reservoir pressure, down to the atmospheric pressure, of course, the oil viscosity will increase. Very simple. And oil formation volume factor as well, you can get. And also gas Z factor, you can get. Gas viscosity. Okay. As the pressure is decreased, the gas viscosity decreases as well. And lastly, produce GOR. Okay, as you go down to atmospheric pressure, of course, the solution GOR will decrease because more and more gas will be deliberated. Okay, and just check the deviation. It's a vertical well, so you have the measured depth against the TVD, the true vertical depth. You can see the plot here, cumulative displacement versus true vertical depth. And the equipment, so this is the existing condition, starting point from here down to this, the end of the tubing. And my tubing has dimension of this, external diameter of 2.875, internal diameter of 2.441, just a template absolute roughness. You can change this value if you have a certain number of it. And casing as well, down to the total depth of the well and external diameter of 5.5 inches, internal diameter 5 inches, absolute roughness of this one. Okay, and temperature model, let's see. So temperature model calculated using the surface surrounding temperature 83 degrees Fahrenheit. Okay, very easy. And you just input this surface surrounding temperature. And ESP data, it's very important. So currently I equip my well with DN 2400 Reda pump with this range of flow rates. Minimum flow rate is 1500, 1500 stock tank barrel per day with maximum flow rate 3200 stock tank barrel per day. I have to 125 stages with the pump is quite old, so the pump wear factor is 0.5. So I have my pump curve here. And the other data, the motor model, the motor that I use, 460 56 PK series, nameplate rating you can see, operating rating 100 horsepower, 55 ampere and 1150 volts. And this is the location of the pump setting depth, maximum equivalent outer diameter 5 inches. It cannot be bigger than the internal diameter of the casing. Operating frequency 60 hertz. Okay, it's already in optimum condition. Upstream temperature 120 degrees Fahrenheit. Okay, so let's see reservoir before we go. So currently I have my well test data to describe the performance of my reservoir. My reservoir is called T reservoir. It's a sandstone reservoir and reservoir pressure 921.7 psia with temperature 180. Middle perforation at this step, water cut is already very high, okay, 99%, but you can still produce oil, you can still get oil from it. But of course, we need opportunity to increase the flow rate, the oil rate. So that's why we want to open another reservoir. Gas oil ratio 300. And I want to construct my IPR using Vogel equation. Okay, and I have my well test data. So I input the well test data to obtain the IPR. So I input my test pressure. In this case, the pump intake pressure. I have the data taken from the downhole gauge. Okay, so the value is 791.7 T PSIA, and I also conduct well testing to measure the flow rate, and I get 1028. So using simple calculation, you automatically get calculated bottom hole pressure of 847.31 PSI. Okay, so you get the productivity index J of 14 stock tank barrel per day per PSI with absolute open flow AOF of 7,231 stock tank barrel per day. So you can also construct the IPR. So the IPR is like this, and your current operating condition is around here. Relative permeability, you can actually skip it. Okay. Many times you can just leave it like this. Okay. Because to construct the IPR, it's actually not very, yeah, don't need to be very detailed, okay, such that you go into very detail with relative permeability. But if you want to input the representative number for the relative permeability, of course you can. Okay. All right. And let's go to analysis. Okay. We want to perform nodal analysis, flow curve. Okay. So yeah, the outlet node, okay, the wellhead pressure 144.7, and the bottom node is at the reservoir depth, whereas the solution node is at the pump intake pressure, ESP. Okay, set range, change it to AOF. I want to construct from 1% AOF to 99% AOF, steps 10, okay, auto range, and you can also click OK, apply and calculate. Okay, so you get the IPR. Okay, IPR, the nodal analysis, the IPR and VLP. So this is the IPR and this is the VLP. So you get the operating condition is this one. Okay, operating pressure. This is the solution at ESP depth, 689.10 PSIA with liquid rate of 2,318. With water cut of 99%, you get oil rate only 23 stock tank barrel per day. And you get this water rate and gas rate as well. At the sand face depth, at the perforation depth, the bottom hole, you also get the calculated bottom hole pressure of 744.76. And you can also check the ESP performance. Okay. We are currently operating here, right? Okay, so you can see. All right. So this one is the IPR. Okay. I mean, yeah, mainly showing the flow rate. Okay. And yeah, this one is the pump horsepower. You can see the value here on the right axis. Okay. This one is the head. You can see here. Okay. So the values will be made gray on the right, so you can focus on the left vertical axis. Okay, for the head, and this one for the pump horsepower, also for the head. Okay, so well bore equipment profile starting from the reservoir pressure here. This is the bottom hole pressure, this is the pump intake pressure, this is the pump discharge pressure, and this is the wellhead pressure, outlet pressure. And this is the temperature profile. Okay, so far so good, and we are currently under 60 Hertz operating frequency. ESP gasiness, no free gas effect. We are currently at this position. Okay, so that's for the introduction. That's our initial condition before adding a new reservoir zone for commingled production. Okay, so what we need to do is like this. So currently we construct the reservoir performance curve based on empirical data. I mean based on the measurement, based on the well test. Okay, if you want to add a new layer, you can click this one, okay? But you will also describe the performance of the new layer using also the test data. Like you can see, we have three options. You input layer parameters, or you input manually, or you input based on well test data. Okay. All right. Either you input manually, just straight inputting the productivity index, or you input the well test data, or you input layer parameters. Okay. Because I now select test data, if I add a new layer like this, I also need to provide well test data. But of course I cannot, because it's a new zone. Okay. It's a new zone. I don't know. I don't know the performance. I haven't opened the well. I haven't opened the reservoir. So I have no well test data. Okay. So of course I cannot know. I cannot predict the reservoir performance of the commingled production. Okay. Using test data to construct my IPR. I cannot. So what I'm going to do is I go back to the existing reservoir, okay, this one, and I need to change the IPR calculation, okay, from test data to theoretical one, which is the layer parameters. Okay, I need to input, so I just go directly here. So this is in this window, we will construct a theoretical model that should mimic the real performance which we have in test data. So I need to input all information, but make sure that the productivity index must be the same, 14, around 14.3. So that by having a model in theoretical model, okay, I can now input the data for the new layer, okay, and then later I can combine them to know the performance for commingled production. Okay, so I just show you directly. So let's deal with the initial reservoir first. Pressure, of course, the same, temperature the same, mid-perf the same. Okay, and now I need to input permeability based on pressure build-up or based on log information. Okay, in this case, I know based on my initial assumption from direct log analysis, the permeability is 195 millidarcies with reservoir thickness of 59 feet and relative injectivity, no, wellbore radius 0.35. Water cut, of course, the same, gas oil ratio the same. Vogel equation 0.2. And of course, we will model also the calculated skin. Okay. And go to drainage area geometry. In this case, I just assume, okay, the equivalent drainage radius 250 meters. Okay. You see, my productivity index is still 0, still cannot be calculated. So I need to provide data for skin factor. Completion type, change it to case hole. I will not model the damaged skin. I don't know anything about this. I have no measurement. I have no laboratory data for this one. I have no detailed modeling to model the damaged skin, so we can skip this one. And now we focus on limited entry skin. So for this reservoir, the nearest measured formation distance is 0 feet. Okay, so the top perforation is located at the top reservoir. So the closest distance is 0 because the top reservoir, the distance between top reservoir and top perforation, 0. Okay, vertical permeability, I assume it to be 10% of the horizontal permeability, so it will be 19.5. open interval, it's 10 feet. So you get the limited entry quite high, 21.8. Well deviation 0. Okay, so it's vertical well. So the deviation skin also 0. And perf diameter 0.37 inches. And shot penetration, we have 3.3 foot, shot density of 6, shot facing of 60. So by using log equation, I get perforation skin minus 0.1172, but actually if you just perform, usual perforation setting, perforation configuration, like this typical penetration, typical shot density, typical shot facing, perforation skin will be around this value. So you see, if I use my data, okay, from the source that I have, the productivity index should be just around 3.44. Okay, it's far from the actual productivity index I get from well test, which is 14.3. So yeah, of course, dealing with subsurface issue, we deal with uncertainty, okay? And in this case, we have uncertainty, of course, in permeability. So that's why you need to correlate the permeability from well log with permeability from pressure build-up, for example, and permeability derived from the well performance, like in this equation. Like in this case, I mean. So in this case, I assume that the uncertainty uncertainty belongs to the permeability. So let's adjust the permeability. Let's say the permeability is 250, and I changed the vertical permeability to be 25, still maintaining the 10%. So productivity index increased slightly. Okay, so I also can assume that we have actually uncertainty in the real open interval. Of course, by design, you know exactly that you want to perforate, let's say 10 feet. But in reality, you cannot be sure how long actually the perforated interval actually resulted. Okay, most of the time the hole will be bigger and bigger, maybe because of corrosion, maybe because of erosion, maybe because of poor integrity. So yeah, we can, generally speaking, we can guess that the open interval must be bigger than 10. Okay, so let's adjust. Let's see if the open interval 15. Now productivity index improves quite significantly. Okay, and let's see if it is 20. Now you get 7.7. Interesting, right? So it's like that. Okay, yeah, it's a challenge with well modeling basically. Yeah, because maybe you also, in the history of the well, you have acidizing, stimulation, you have water flood, so the permeability will change. Okay, 300, let's say. So skin factor, I mean the vertical permeability, 30, 10% of the horizontal permeability. Okay, and let's see if the open interval is 30. Now you get 13. Okay, so now we are very close to the, to the real productivity index. Okay, of course, you can also adjust like drainage area if you want. For example, it is 200, but you see, it's not significant. The change is not significant. Okay, it is, let's, it's only 100 meter, but I don't think it's the correct number. So you can also change to 150 if you want. But I think the 250 is a good number. Okay, and yeah, maybe 200. Okay, for argument's sake. Okay, 200. You can also change to rectangular if you want, but of course there will be more issues, wedge shape, okay, and go back to circular to make it simple. Okay, so yeah, 310, 31. Okay, we are closer and closer to the real value. So what if we also assume there will be uncertainty in the perforation diameter, for example? Okay, let's check. 0.39. Okay, you see the change is not significant. 0.4, right? Shot penetration, for example, 4 feet. You see 5 feet. Okay, 6 feet, 7 feet. You see, no change, no significant change. So you see that if you want to get the same number, 14.3, which you get from well test, yeah, we need to adjust the permeability in this case. So let's see 32. Okay, so let's see we can take this 14. Okay, and you can also click save. So you see now the productivity index is very close with the actual performance I get from well test data. Okay, so the absolute open flow 7,000. So with the same method, okay, I want to construct IPR, okay, for the new reservoir. Okay, so let's go to new layer and I call it B layer. Okay, it's active and it's a limestone reservoir. So now let's input what I know about this reservoir. Okay, so the value is this reservoir temperature 180 and the mid perf at this location. And I know the permeability 243 based on well log. Thickness is quite thick, 80 feet. The same, of course, wellbore radius. Water cut, let's say, I know, I predict the water cut to be 97%. Gas ratio, 300. I want to construct, of course, using Vogel approach, 0.2. And I use calculated skin. Drainage geometry, 250. Or maybe based on that, 200. Okay. And skin modeling, case hole, limited entry skin. Okay, the nearest measured formation distance 1.35. So vertical permeability, maintaining 10% assumption, 24.3. Upper interval, 20 millidarcies. Deviation skin, 0. And the same configuration for the perforation, 3.3. Shot density 6. And shot facing 60 using log equation. Okay. So 3.3, 6. Can save. You can go back to test data or maybe layer parameters, skin, something wrong here. So that's why the perforation skin still none here. Just change it to, okay, so, oh, this is error. So this is 1.35. Okay, so now you get the perforation skin, okay, and the productivity index 7,007, I mean 7.77, okay, lower than the previous one, I mean the initial reservoir. And we get absolute open flow 3,400, and this is the total Darcy skin. Okay, so now I have two reservoir, my existing reservoir, the T reservoir, and now I also have my target reservoir, the B reservoir. I want to combine the performance between them both, and I can show the composite IPR using this one. Okay, so very interesting. You can also show the legend here. So this one is the T reservoir, the performance for the T reservoir, and this one is for the B reservoir. You can see the T reservoir has greater reservoir pressure, so it's bigger in size, and it has better quality. The, the PI, the productivity index, is 14, whereas you also have a B reservoir. It's actually not a poor quality reservoir. It's good reservoir, but the reservoir pressure lower and with slightly poorer quality. And if you combine them, if you perform commingled production, you will have this new IPR, the green, I mean the blue IPR. I can make it bolder, okay, just to appreciate it. Okay, so this is what you have if you perform commingled production. All right. Okay, so there is no risk of crossflow between the two reservoirs. So in general, you obtain a better performance. Okay, you get a better performance in liquid production perspective. We still don't know about the oil production perspective because we have different water cut. Okay, so that's it. And by maintaining the same configuration for the ESP, let's say we assume everything the same for the ESP, the pump stage, the pump type, the pump setting depth, okay, and so on and so forth. We just go directly to the analysis. We perform nodal analysis. Okay, so just calculate. And what do we have here? Okay, so by combining them, okay, by combining the two reservoir, we get improvement in oil rate. Previously, if I'm not mistaken, the oil rate was 23. 23 because you have water cut of 0.99. And after you combine them and the new reservoir has lower water cut, you get at the end oil rate of 337 with water cut of 0.985. Okay, you can also make it like this. So that's it. If you maintain everything the same, all right, if you maintain everything the same, you will get oil rate of 37. Okay, 37 stock tank barrel per day. So at the, yeah, later you need to perform economic analysis and also production for forecast if the existing reservoir already reached water cut of 99%. Are you sure that you want to keep the reservoir, or maybe you want to just isolate the layer because it's already very water out, 99%. Maybe just tomorrow you reach 100% water cut, so why bother keeping it open? Okay, maybe you can just isolate using bridge plug, or maybe you just squeeze cement the layer and just go to the new reservoir with lower water cut. All right, so that's it. That's that's how we do the prediction for this commingle production. And of course, we can also do sensitivity analysis. Let's say I'm not sure that the water cut in new layer only 97%. Maybe it's even lower. Okay, so let's see sensitivity water cut. Okay, it's this one 0.6. Let's say, and you click add sensitivity water cut. Okay, and you just calculate. Plot variables, sensitivity variables, click on OK, and flow curves. Yeah, in this case, you just input directly. Okay, there is no option to assign this water cut to B reservoir, to the new reservoir. No, in this case, I cannot, unfortunately. So I just put a number and then just assume that it's the mixture water cut. Okay, but yeah, but let's just input 0.98. Let's say by opening new layer, I can achieve 98% water cut. What is the flow rate that I get? If I get, after commingling the production, I get the water cut of 98% as opposed to 98.5%, I can get the flow rate of 49, okay, which is, yeah, even greater than the previous oil gain of 37 barrel oil per day. Okay, so you see the point. Because you open a new reservoir, okay, a new reservoir, you will get better water cut, hopefully, because it's a new reservoir, okay, that hasn't been opened. You expect water cut that is lower. In this case, the new water cut is actually already quite mature and it also reaches high water cut, but we believe that it's still lower than 99%. Okay, so that's it. The uncertainty in this case is the water cut. And also don't forget that you have uncertainty in the case of permeability and the open interval, perforation interval. But as far as modeling commingle production is concerned, we have done that. And this is what we have. Okay, you add new reservoir, you need to construct the IPR of the existing reservoir and the new reservoir, and you get the IPR of the commingled reservoir, and then you just bring them into nodal analysis and just do sensitivity analysis, for example, for the water cut. Okay, so I think that's all. I hope you enjoyed this video. I hope this video is useful. Thank you so much for watching and see you again in the next WellFlo videos. Thank you.